So this is problem 53 in chapter 8. Okay, so here, I'll rewrite it down here. Cl, CH2, 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 S minus. And then what happens is this sulfur is going to cyclize onto itself intramolecular. We saw this, I did a few homework problems, except it had an oxygen atom. And then I believe on the exam I had a problem like this as well. So it cyclizes on itself and you form the ring compound. All right? Does that make sense, Ashley? Makes sense. Yep, no problem. All right, anybody have any other questions from homework? It'd be great to do some homework problems if you like. Chapter 8. I think we did a bunch last week. And then on Thursday, we did a lot of problems, which I think was pretty helpful for some people. Okay. All right, anything else? Any other homework questions? Otherwise, I'm going to start chapter 9. All right, let's start chapter 9. All right, let me just open my notes real quick, just so I got. All right, so like all of them, I'll go through the slides. If there's any questions that you have about the slides or from the homework, just stop. Feel free to stop. Either type it in, excuse me, or undo your microphone and talk into it. That's sometimes a lot easier and quicker. Because again, I might be like 3 slides ahead, and you're still trying to type something. All right. Pen. Again, I'm trying to navigate all these different windows. I don't know where to put this. Actually, I don't need this anymore. I just want to keep the chat box available so I can at least see that. Put it up there. Okay. There we go. If you watch the the videos I make, you can see what I actually see right now. Like, you guys can't see my chat box and all the other stuff, but when you watch the videos, you can see all the clutter that's on my screen here. All right, aldehydes, ketones. That's what this chapter is going to be about. We know what an aldehyde and ketone is. These are just some real-life compounds. Here's hydrocortisone. The structure of hydrocortisone is a ketone. It has 2 ketones. It's a steroid. It's a type of steroid. All right, so carbonyl compounds. A lot of compounds in organic chemistry deal with carbonyls, so kind of an important type of compound. This stuff we don't really have to go through too much. All right, here are just the types of carbonyl compounds. This is chapter 9, the stuff right here. This is chapter 9. All of this down here is chapter 10. So chapter 10, we'll start learning about carboxylic acids and a carboxylic acid derivative. These are all of the derivatives of carboxylic acid. So in place of an H, you can have a halogen, you can make an ester, you can make a thiolester, an amide, an acid anhydride, and acyl phosphate, which are not things that we'll see in this class, but if you take a biochemistry class, you see a lot of these. Okay, you'll see a lot of these types of compounds. Okay. All right. So we know this stuff. Carbonyl. This is just review from chapter 1, I think. There you go. So you've got a carbonyl, partial negative, partial positive. You've got a pi bond here, so it's kind of showing you the pi bond right here. Here's the pi bond, and then it's 2 lone pairs. All right, for naming aldehydes and ketones, we'll go over this a little bit, and then we'll do a practice problem. So there are some common aldehydes and ketones. These are kind of the common ones. Formaldehyde is kind of it's the one exception as to what an aldehyde looks like. So what we talk about aldehydes is anything that has a carbonyl and a hydrogen. Usually this is a carbon, but in one case, in the formaldehyde case, you have two hydrogens on either side. All right, so that's formaldehyde. Acetaldehyde is just one where you have a CH3, so a 2-carbon fragment. All right, all these other ones, these are not things that we'll talk about. Here's a benzaldehyde. A benzaldehyde actually smells like almonds. All right, in fact, there's a lot of benzaldehyde in almonds. That's what gives almonds its smell, is the benzaldehyde. If we were still in class, I would actually go in the stock room and get the bottle of benzaldehyde and pass it around. You can smell it. It's so concentrated, it has that artificial almond smell. So like marzipan. I don't know if you guys know what marzipan is. It's like that. It's like that candy. It's like the doughy candy that's always in shapes of like fruits and animals and stuff like that. My wife loves it. There's some people that just love to eat that. I can't stand it. It's just way too much almond flavor for me. But that artificial flavor in it is benzaldehyde. So these are just some common ones. Okay, so in naming, it looks like naming ketones first. So naming ketones, everything ends in -one. So you're going to drop the E in the name. So if you have like hexane, you drop the E and end it in -one. So hexone. All right, and you also have to tell the reader hexanone. All right, and you also have to tell the reader which carbon the carbonyl is on. All right, so if you look at some examples here, also you start counting on the side closest to the carbonyl. So number begins the end near the carbonyl. So on the third carbon, we have a ketone. So here's the new way, which is the way that we're going to name things. Let's not worry about these up here. So it's hexane, we said 6, and on the third carbon, we have our ketone, 3-one. All right, you can also have what's called an enone, which has a double bond and a carbonyl. These are very common types of compounds, especially if you have a double bond next door to a carbonyl. That's usually the more common setup. Here I don't have it. Here you have it like 2 carbons away. And the reason is because you can actually have a resonance structure with these alternating double, single, double bond. So this is a very stabilizing effect on these types of enones. So enone. En meaning a double bond and one meaning a ketone. So you'll see these a lot. It's called an alpha-beta unsaturated. Either a ketone or aldehyde. That's basically called an alpha-beta unsaturation. That's because the carbon next to the carbonyl is called the alpha carbon, and the one below it is called the beta. All right, so alpha-beta unsaturated. It's unsaturated. So remember, unsaturated means I have a pi bond, pretty much. Saturated means I don't. So these are very common types of. It's not really a functional group, but you see them a lot. All right, if you have a diketone, just start counting the closest side to it. You just name dione. But again, you have to tell the reader where the 2 carbonyls are. All right, here's some common ones. Acetone is obviously a common one. Acetophenone, benzophenone. These are some common ones. We're really not going to look at it as groups hanging off. Didn't actually have practice problems. Thought we would do a practice. You know what? Let's just do. Go to the book. Let's find some practice problems. Oh yeah, actually on those Thursday, right, where I was able to copy and paste them in, that actually worked pretty well. All the structures, let's name them. Let's do D. do D. Actually, let's do A and D, because that has both, and you know, a lot of stuff in there. So A and D. Let's see if I can. The whole thing. I don't know if you guys can hear my bird in the background. You guys hear the bird? I have a parakeet that just squawks crazy. All right, you guys need more time? Hit Y if you need more time. Hit N if you do not need more time. Okay, Ashley needs. All right, I'll give you guys more time. It's just you, Ashley, and Lucas. No rush. Okay, Ashley's done. Good to go. All right. Okay, so the first one. Oh well. Okay, so the first one. Okay, so we're going to start counting from the carbonyl. That gets priority. So that's going to be carbon 1. And then I'm going to go the direction closest to our double bond. So 2, 3, 4. If we did it this way, 1, 2, 3, 4, that's equivalent, but I have the methyl group. So this carbon is closer. So I'm going to go that direction. All right, so this is, notice it is also an enone. Okay, now for a cyclical, a cyclical compound, you don't have to tell the reader where the carbonyl is. If you want to, that's fine, but you don't actually have to because it's always carbon 1. So I'll do it both ways. I'd be fine either way that you do it. So it'll be 3-methyl, and then you're going to have a cyclohexene, hex 3-enone, or you can name it hex 3-1-one. Chat box is in the way. Okay, so either way is fine. All right, any questions on that one? 1, 2, 3, 4, 5. All right, I'm going to start counting on this side. Because it's close, so the carbonyl is equal, like 1, 2, 3, or 1, 2, 3. So then I'm going to, my next priority becomes whichever side has the closest substituents. All right, so we have 2-methyl, and this will be a pentan 3-one. All right, good, straightforward. All right, preparing aldehydes and ketones. So this was from the last chapter. We have learned that, so this is PI, this compound right here is PI, or PCC will make aldehydes or ketones. If you want the aldehyde, you have to use PI and PCC on a primary alcohol. All right, we're not going to worry about this. This is dival. We didn't really learn this last chapter, but this is a way to go from an acid or ester to an aldehyde, but I told you guys that there is no way to do that, so we're going to pretend it doesn't exist. Because dival, you have to, the moon has to be in a certain phase, and it's very tricky to use this compound. So let's ignore that. I wish it wasn't there, because they don't really talk about it even in the book. And all of a sudden, it's there. So we're not going to worry about that. If you want to make an aldehyde from an acid, you got to reduce it all the way down. So if you have an acid, just to remind you, you have an acid, you got to reduce it all the way down with LAH to the alcohol, and then you add like PI or PCC, and you can get it to the aldehyde. Okay, but preparing aldehydes, primary alcohols plus PI or PCC. Okay, so here's just an example. If you want to get ketones, you can use any of them. PCC, PI, the CrO3 in acid, or the Na2CR2O7 in acid too on secondaries. All right, we also learned if you take a triple bond, you can add that mercury and acid. Remember, this is a chapter 4. This is chapter 5. These are just review reactions. Okay. Okay. So these are all review. This was last chapter. This is chapter 7. Either oxidize it up. Okay. This we also kind of learned. You can also, so these are reactions of aldehydes. So we learned again, if you take an alcohol plus the CrO3 in acid, you can get the carboxylic acid. So remember, it goes straight to the carboxylic acid. So we talked about the oxidation steps: alcohols to aldehydes to a carboxylic acid. Okay. So if you want to go from an alcohol to a carboxylic acid, you add that CrO3, all right, or Na2CR2O7. Okay. However, what if you're starting at the aldehyde? What if you're starting here and you want to go to the acid? Well, it's the same reagents, okay, because the alcohol to the acid actually stops in between. It stops at the aldehyde and then it keeps oxidizing it. So if you just start at the aldehyde, you can do the same thing. Oxidize the aldehyde up to the acid using the same ingredients. So even though they have a slide or a section in the book about this, you already know this. This is something that we learned last chapter. All right, here it just kind of shows you how it works. This is kind of a mechanism. I'm not going to ask you about this. If you're interested in learning about it, you can go ahead and look at it. Okay? Section 9.5 now talks about once you have an aldehyde or ketone, what kind of reaction can you do on them? All right, and you can do what's called a nucleophilic addition reaction. So what's a nucleophilic addition reaction? Well, you add a nucleophile. That's, add a nucleophile. Pretty straightforward. So you have a carbonyl, partial negative, partial positive. You're going to add some sort of nucleophile, all right? So it's going to have a negative charge associated with it, all right? And just get that out of there. I hate how this does that. It's just a glitch in them. So basically, this nucleophile is going to come in here, add into your carbonyl, and kick up the pi bonds. So most of your intermediates are going to be nucleophile. So this is just a general mechanism. It doesn't always do this. There are a few other examples where it does something a little different. And then usually a second step is to add acid, because you have to protonate that alcohol at the end. Okay, so like last chapter, our nucleophiles were hydrides. If you remember, we were using hydrides and adding them in there to reduce the ketone or the aldehyde or ester or carboxylic acid. All right, so here's just a general mechanism. It's the exact mechanism I did on the last page. Nucleophile attacks, kicks up your pi bonds, just like I did here. Nucleophile attacks, kicks up the pi bond, and then you add an acid of some sort to protonate your O negative at the end, and you form an alcohol. All right, here's just an example of strong nucleophiles. We know this. Why are these called strong nucleophiles? Because they all have negative charges associated with them. All right, hydroxide, hydride, carbon negative. We'll learn a lot about this type of molecule in this chapter. All right, cyanide. You also can use the acetylide. Guys, remember the acetylide? That's the acetylide. Chapter 4. And then here are some of the weaker ones that use an acid environment. All right, so this is basically the general mechanism. We talked about this, the general mechanism of reducing a carbonyl with either LAH or sodium borohydride. You just use a hydride of some sort and add in there. So that's our first step. Our second step is adding acid. Again, this is chapter 7. This should be review. There's nothing new here. All right, I want to talk about Grignard reagents. That is the big one. Let me just see what there is here. I think I'm just going to do my own slide. Yeah, I'm going to do my own slide on this. All right, Grignards. Victor Grignard won the Nobel Prize for this. That's how big it was. I believe in 68, 67, 1968, 1967, something like that. Greg. Spelled it wrong. All right, Grignard and Grignard reagents. All right, this is basically a carbanion. Now, we've learned about one carbanion. That's the acetylide ion. Okay, remember I talked about it's the holy grail of reactions. Anytime you can get a carbon negative, you form a carbon-carbon bond. That's kind of a big deal. Well, that's what Grignard did. All right. Now, the carbanion. Now, this is not a Grignard. That might be confusing. This is not a Grignard. This is just to remind you. All right. This is just on an sp carbon. Grignard was able to make carbanions on sp3 and sp2 carbons. So that now any type of carbon, any molecule can be turned into a carbanion. Before, you can only do it with a triple bond. All right, kind of, so if you wanted to make a carbon-carbon bond, you'd have to use a triple bond, make it, and then you'd have to alter this somehow. Grignard came up a way where you can use any type of carbon you want. That's kind of a big deal. Okay, so that's why he got a Nobel Prize for this. Okay, very useful reaction. People still do it, like today. If we didn't have this social distancing, people right now at CSU would be in the chemistry lab probably making a Grignard. I mean, they're made all the time. All right, I probably made over 100 of them when I was in grad school. Right, that's how common it is. All right, basically in order to make the Grignard reagent, let's talk about the Grignard reagent, and then we'll talk about what you do with it. What you do is you take an alkyl halide of some sort, and again, it could be sp3 or sp2. I'm going to put an X here. Remember, X is a halogen, chlorine or bromine or iodine. All right. You can use any halogen, and you add magnesium metal. You actually add the metal. I'm going to put a solid here. It's just the metal. If you've ever seen magnesium, it's like a white, silvery type of metal. And you mix these two. It has to be very dry, meaning you can't have water in it. And use a solvent. Usually the solvent is what's called THF. You don't have to worry about this, but you might see it in the notes, not in the notes, but on the slides or in the book or something. This is usually the solvent that's used. As far as I'm concerned, you don't really have to worry about it. But if you see that THF, that's the solvent. It stands for tetrahydrofuran, which this is the structure of tetrahydrofuran. So that's actually the solvent. And actually, the oxygen actually helps stabilize the actual Grignard, but that's more information than what we need to know. And what happens is the magnesium inserts itself between the carbon and the halogen. All right, so that's what happens. The magnesium goes in between the carbon and the halogen. All right, notice we have a metal here. So what type of bond do you have when you have a metal attached to a nonmetal? It's an ionic bond, right, where the magnesium has the charge. So what happens when the magnesium inserts, it actually creates this negative, actually now has a negative charge. It has a lone pair with a negative charge, and the magnesium is the counter ion for it. Put a plus charge here. So this is really the way that you should think of a Grignard. Right? Don't actually think of it as a bond, because it's not really a bond. It's an ionic charge between your carbon and your magnesium. So you have your negative charge, which is your carbon, which is our nucleophile, and then you have magnesium, which is the plus charge. So that's what a Grignard reagent is. It's a carbanion, right? Carbanion, carb meaning carbon, and then anion meaning negative charge. So it's got these lone pairs, very, very nucleophile, very strong nucleophile. So that's what a Grignard is. Okay, so what do you do with Grignards? Once you have formed the Grignard, now I'm going to write Grignards for now on without the magnesium, because the magnesium is the counter ion. It's not the important part of it. Well, Grignards in this chapter are going to add to carbonyls. You can either have an aldehyde or a ketone. So let's put ketone or aldehyde. Okay. Remember, you have a partial positive on this carbon and a partial negative on that carbon. So this negative charge is going to add right there and kick up the pi bond. So this is the mechanism now of what Grignards do. So you've made a carbon-carbon bond. This is the bond that I just made. Okay? At carbon-carbon bond, there's a carbon attached to another carbon, so I made a carbon-carbon bond. All right? And then the second step is, again, always adding acid to protonate your O negative. You guys hear me all right? Is everything all right? I just got a message saying that there's a problem connecting to the network. Just want to make sure you guys can hear me and all that stuff. Connection is bad. Okay. You guys able to hear me now and all that? I'll tell you what, I'm going to turn off my video. There's no reason that you guys have to see me. Alright, is that better? Worse? I mean, I'm recording this too, so you'll be able to hear everything. Is that better?
No.
Yes or no? Maybe it's not, because you guys aren't saying anything. Oh wow, here we go. We only got everything frozen here too. Where did you go, Steve? Left. Oh no. You guys hear me? Yes. Okay. All right. Okay. Good. Okay. I got all this stuff late. That's what happened. I just got all of your chat now. Okay. Now we can. All right. Good. All right. So add the acid to protonate it to give you OH, and then your carbon down here. Okay. So basically, what happens is what you're getting is you're forming a carbon-carbon bond, and you're making an alcohol at the end. So Grignards, in this case, so a Grignard makes a carbon-carbon bond, and it makes an alcohol. Okay? So, let's go back to these slides. I don't really give a lot of examples on this. Okay, so let's do some problems here. All right. Let's take CH3Cl. I'm going to put a list of reagents here. So the first step is adding magnesium. Actually, I'll tell you what. Let's just do this. Magnesium. Show me what the product is. Then add cyclohexanone to it. Show me what that product is. And then add acid. And show me what that product is. So we'll do it stepwise. Okay? So I'll go on mute and I'll turn off the mic and I'll come back in about 5 minutes. All right? All right. You guys need more time? Or are you guys good to go? If you're good to go, hit yes. If you're not, hit no. Yes? Okay, good. All right, good. All right. Okay, so the first step is making the Grignard. So you're going to form CH3MgCl. All right? You can write it however you want. If you want to write like that, if you want to write it with the bonds, that's fine. If you want to write CH3 minus with MgCl plus, that's fine. All these are fine. As long as, you understand how it's supposed to work. All right? And then the carbon group, the methyl group, is going to attach itself to the carbon that has the carbonyl. So you're going to have that. Let me erase this a little bit. Okay? If you're wondering about the magnesium and the chloride, well, remember I have a negative charge here. Remember, a negative charge can't exist by itself. It has to have a counter ion. That's what our counter ion is the magnesium and the chlorine is now the counter ion for the O-. Again, you don't have to show me. I don't really care about it. But just in case you're wondering where all this stuff goes, once my carbon adds in here and forms the O-, the magnesium and the chloride now are the counter ion for that negative charge. Okay? And then the next step is adding the acid. And so you form CH3, and you'll have an OH right there. Okay? So you form that methyl cyclohexanol. Questions? Good. right? Garrett, I can't hear you. I heard a little static, and then all of a sudden it went gone. So if I want to try again. Yeah, you're okay. You want to try to talk now, Garrett? Yeah, I can't hear you. Yeah, I hear a little bit of static, and then it's gone. I hear a psh, and then it's gone. Jacob, yes, there is stereochemistry. In this particular example, there won't be because it's achiral, because this side of it is exactly the same. But you always get a 50-50 mixture because a carbonyl compound is planar. So let's just say, I don't know, you have like that compound. All right, it's a planar molecule. So the Grignard can either attack from behind it or in front of it. So you technically get a 50-50 mixture of that alcohol. Okay. Now there are ways that you can take Grignard and make them one or the other enantiomer, but that's more advanced stuff. All right, Garrett. If there's more than pi bonded one oxygen, does this reaction happen multiple times? So you can't have more than one pi bond attached onto an oxygen, because if you did, then you would have 3 bonds onto oxygen, and oxygen it can only have 2 bonds. So you can't have more than one pi bond. So you either have a single bonded oxygen or you have a double bonded oxygen. You can't have a triple bonded oxygen. But you can do this on a nitrile. There are ways you can do it on nitriles, which I believe our next chapter, they talk about this. So you can have a nitrile and add a Grignard to it. So we'll add once to form what's called the imine. You get an R group, and then you can actually add a second one and add it again, and to form like 2 R groups. Also, esters, you can add them onto esters more than once, but again, we will learn more about that next time. But as far as this particular answer, oxygen can only have a double bond, but you can add Grignards multiple times if you have a different functional group on there. So I think that's kind of what you meant more in that question. If you have more than one pi bond, can you add it more than once? No, if there was more than one pi bonded oxygen. Oh, I see what you're saying. If I have like 2 ketones on my molecule. Yeah, there is no way that you can actually control it. You would get a mixture of compounds. So if you had like a ketone here, and then if you had, like a ketone here, all right, and if you added a Grignard onto it, if you added like 2 equivalents of it, yes, I can add it onto both. But if you just add one equivalent, it would not select one ketone over the other ketone. You get a mixture of compounds. Okay. Does that answer, Garrett? And then 2587, Andrea. Yep, Andrea. That's correct. You cannot have an acidic proton when you add a Grignard. So if you have a carboxylic acid and you add a Grignard to it, the first thing that this is going to do is pluck off that proton, and it's called quenching your Grignard. You basically quenched it, because if you think about it, if you have, let's say you've got a methyl Grignard and it grabs a proton, you basically just form methane gas, and it gets rid of the Grignard, and it's gone. So yeah, you can't have any type of acidic proton. You can't have any acid or water or anything like that. So Grignards are only able to be added onto ketones, aldehydes, esters, nitriles, things like that. But if you have an alcohol in there, it will quench the Grignard. If you have a carboxylic acid, if you have an amine, it will quench the Grignard. I think the slide actually does show you some common groups. Here you go. So here are some common groups that Grignards do react on. So aldehydes, ketones, amides, as long as you don't have any hydrogen on the amide. Nitriles, NO2 groups. These groups, says, see, a Grignard reagent is protonated by these groups, so meaning quenches it, which would be an alcohol, an amine, a thiol, a carboxylic acid. Yeah, so Andrea, this slide kind of answers that. Yep. All right, let's do some reaction problems here. Use a Grignard reaction on an aldehyde or ketone to synthesize the following compounds. Last week, this was an error. I was able to highlight this. Why can't I find that now? Oh well. Okay, so let's see. Which one should we do here? Let's do A and B. Do A and B. Oh, maybe. All right, let's go back. So do A and B. So use a Grignard reaction on an aldehyde or ketone. So you choose what aldehyde and ketone you want to use to form these compounds. So either pentan-2-ol or 1-phenyl-butan-2-ol. All right. Again, put this on break, and then hey everybody. All right, let's start back. All right, so use a Grignard reaction on an aldehyde or ketone to synthesize the following compounds. So pentan-2-ol. Okay, that's pentan-2-ol. So what Grignard reaction would you do to make that? Now, there are two possible answers. All right, anytime you have a carbon with the alcohol on it, and you're doing a Grignard, you can either make this bond, compound A, or let's do a different color here, or you can make that bond. Let's say that's route B. All right, so let's first make route B. All right, so basically this would be the Grignard, those three carbons. So I would have, and then Mg, let's say Br, you can have Cl, whatever, but basically it's three carbons. And then your aldehyde group would be these two carbons right there. So you would have a carbonyl and then a hydrogen. So these would be the two reagents that you would use. So the propyl Grignard, this is called propyl Grignard because it's three carbons, so it's propyl Grignard. And then you would add, let's see, there's three here, the acetaldehyde, right? And this carbon right here would be making the bond right there. All right, that's the blue route. To make the A route, this is the Grignard. So in that case, it would be just a methyl Grignard. And I'll put a chlorine here, but you could, again, you can put any halogen you want. And then this becomes the aldehyde. So 1, 2, 3, 4 carbon aldehyde. 2, 3, 4. And then okay, so there's two possible answers on that one. Any questions on that? No questions? All right. 1-phenylbutanol. Phenyl 2-butanol. Is that what it is? Make sure we got it right. 1-phenyl 2-butanol. Right. Okay. So I think I told you last time that pH is a shorthand for an aromatic ring. So rather than writing the whole aromatic ring, you put a pH. So just to remind you, this is the same thing as this. So this way I don't have to keep drawing, because you know, it's hard enough to draw these on this pad. It's a nightmare. Okay. Oh, sorry about that. Someone's calling me. King Supers is calling me. That's nice of them. We have toilet paper. Please come in. Yay. No, I don't think that's what they're calling me. Okay, so anyways, there's the compound. So we have to make this compound. So again, there are two possibilities. You can either make that bond right there, or you can make.
Hello, this is a courtesy call from your JFK Parkway King Super Pharmacy. We are calling to let you know your prescription is ready for pickup.
That's great. Thank you.
If you have any questions, speak with our pharmacist. Please call.
Sorry about that. Just do the rest of it. Okay, so either one of those. All right. So if we do the red route. All right, if I'm making this bond, this is the bond I'm making on the red route, right? These carbons are the Grignard part of it. So let's see, MgCl, CH2, CH3. And then this side of it is going to be the aldehyde side. So I'll just put pH again, and then aldehyde. So those would be the two fragments. Okay. All right. Can you guys give me a sound check? Just in case, I just want to make sure you guys can hear me and everything. Just hit a yes if you can hear me. Okay, good. Just want to make sure. You guys didn't laugh at my jokes, so I was wondering if you were there or not. They were pretty good ones too. All right, and then the other. Let me let's see. Where's the? Let's just delete everything. All right, and then the other possibility would be, let's turn it back to blue. This would be the Grignard, so pH, CH2, MgBr, and then this would be your aldehyde. In this case, aldehyde. So in all cases, they're aldehydes, but you can use ketones depending on. So if you have a secondary alcohol, it came from an aldehyde. I don't know if this helps. If it's a tertiary alcohol, it came from a ketone. Okay, so like if you have because for example, let's just give you a ketone here, and then let's just add methyl Grignard to it. All right, notice you already have two carbon groups on your carbonyl. Your other one's going there, so you'll get a tertiary alcohol. So ketones give you tertiary alcohols when you do Grignards. Aldehydes give you secondary alcohols. Okay. But any questions on these two? You guys get it? All right, good. Just okay. I think we're good. Let's continue on with the lecture. There's a few more reactions. Okay, next reaction. This one's not really a reaction you need to know. It's just kind of showing you because it's going to help you understand the next actual reaction we care about. But you can actually hydrate a carbonyl. So if you take a carbonyl plus water, the water actually adds. So your oxygen can actually add here and kick this up. And you get a proton transfer step. And you form what's called a carbonyl hydrate. This is reversible. Mostly, this arrow should exist like this. So it is in a little bit of an equilibrium where most of it is in the form of the aldehyde or ketone form. Okay, a gem diol is where the alcohols are on the same carbon. It's called a gem diol. Okay, where the OHs are on the same carbon. Okay, so this is just a hydrated form of a carbonyl. So if you have a little bit of water, if you put a little bit of water into a ketone or aldehyde or something like that, well, it's mostly ketones or aldehydes, you get a portion of it forms this kind of hydrated form of a carbonyl. Okay, and it just kind of shows you a mechanism here, a general mechanism of it. I'm not really interested in the alcohol version. I care more about in the water version. I care if you have an alcohol. Okay, so if you take an aldehyde or ketone and add an alcohol, so if you add one equivalent of an alcohol, you form what's called a hemiacetal. Hemi in this case implies half, because an acetal is where both groups are OR groups. Right? Notice you have two OR. Hemiacetal is when one group is an OH and the other group is an OR group. And again, it's on the same carbon. This is called a hemiacetal. If you add a second equivalent of alcohol to it, then eventually that OH goes away, it comes off as water, and you get this OR group to actually go on there. Okay, so here is the mechanism. I want to do my own mechanism. I don't like this one's in here. So let's say you have some sort of let's say we have a ketone, and you are adding, let's do a different color. Let's do green. I like the darker colors. So let's say we're adding ROH to it. Okay, and you're in the presence of acid. All different colors. Okay. So what the first step is, we'll do the arrows of black. The first step is the oxygen protonates itself with the acid. Okay. So you form this, and it protonates itself. Okay, the reason it does this is because it makes this carbon more nucleophilic. All right, you have a much bigger partial positive charge on that carbon now, so that your oxygen can actually react. Okay, so now your alcohol can actually add into there now and kick these electrons up. Okay, so the first step is protonation. All right, remember on this oxygen here, you have lone pairs. So the lone pairs are going to protonate to give you this positively charged oxygen. All right, oxygen's not happy with the positive charge. It's tugging on these electrons because it's more electronegative, making this carbon very partial positive. So the alcohol oxygens are going to add there, kick up the pi bond. Notice you have a proton here. All right, so in a way, if you look at this, this is kind of the hemiacetal. You have the OH group. So you have the OH group right here, and you have the OR group right there. Remember, an acetal, just to remind you, acetal is OH, OR. That's a hemiacetal. Okay, but this is going to go further. You usually don't stop at the hemiacetal. It's just kind of an intermediate step. Okay, but what's going to happen is this oxygen is going to pluck off this acidic proton. And these electrons will go onto that oxygen. Okay, so why do we do that? What are we forming? And we've talked a lot about this. We're forming a water molecule. Okay, so this OR group is still here, but all we did is this proton right here got transferred onto the oxygen over here to make a water molecule, because we know water is a good leaving group. So what's going to happen is these lone pairs are going to pop back down and kick out that water group. So water leaves, and now this compound is going to look like this. Okay. So I got one of the OR groups on there. Now I just have to get the second OR group on there. So another equivalent of ROH, let's do green, consistent with the colors. Adds in here, kicks up those electrons, and you now get OR, you'll get a OR with an H with a plus charge, and then you still have your two carbons here. And then you have a water molecule pluck off that last acidic proton, because this acid over here is a catalyst. So remember, if you use it, you have to regenerate it at the end of the reaction. And we're forming, notice H3O plus here, which remember is the it's the same. Oops. So that's your acetal. That's how you form your acetal. Just a bunch of proton transfers. And so every other step is what we call a proton transfer. So this first step is a proton. We're transferring a proton onto the oxygen. Then we have a nucleophilic attack. Then we have a proton transfer. Then we have the pi bonds form and the water leaves. And then an attack. And then a proton transfer. So you can always see there's always these proton transfers all throughout. All right? So that's how you form acetals. So the overall reaction, you guys are right if I delete this? You guys still need it? I need to get more room. Yeah, okay. All right, so the overall reaction, just to remind you what the overall reaction is you have some sort of a carbonyl. You're going to add, I'm going to put two equivalents of ROH, whatever your alcohol is, in the presence of acid. Now, the book sometimes is confusing. They don't clearly say one equivalent or two equivalents. I don't think they do. I remember them. So you kind of have to just, if I don't write anything, assume it's two equivalents. All right. If I don't say one or two, assume it's two. If I clearly say one equivalent, then you stop at the hemiacetal. If I say if I don't say it, then assume it's two. You see this problem right here? They don't say one or two, but they do tell you, show the structures of the intermediate hemiacetal and the final acetal. So in this type of problem, you're kind of showing both of them. You're showing the hemiacetal and the acetal. Okay? So why don't we do this problem, 34A, all right, 34A as a practice. Can't do it. Okay. All right, so do A, problem A. I'll actually copy it down over here so that you guys can get it. Let's see, it's the propanol and acetalphenol. Again, I'm going to put shorthand. Okay, so show the hemiacetal and then also show the acetal product. You don't have to show the mechanism, you're just going to show me what the products are. Okay, so the hemiacetal. You know what? Let's do different colors, just so. Because sometimes it's hard to follow this. So let's do this alcohol in different colors so that you can see. Which color? You know what? Let's do a purple. That's purple. Yeah. Everybody likes purple. Who doesn't like purple? So the hemiacetal still has the OH, and then you will have your purple isopropyl right there. That's the hemiacetal. Right? And then the acetal. Look at that. Okay? These, might be thinking, where are these found? Where do you see these? Your book talks about how they're used as protecting groups. So, like, if you want to do a reaction. So, actually, Garrett asked a question earlier, where if you have two different carbonyls, will the Grignard attack both of them? And I said, yeah, but it can attack any one of them. It doesn't have a preference, but sometimes what you do is if you add a acetal, you can actually only react the acetal on one of the groups and use it as a protecting group. So it protects that carbonyl so that you can do a Grignard on the other carbonyl, and then you can take off the acetal. Because in order to take off the acetals, if you just add acid and water, it does the reaction in reverse, and it reforms your ketone compound. Plus, you get the two alcohols afterwards, which I don't really care about that part of it. But if you want to get rid of the acetal, just add acid and water, and it reforms what you started with. Okay, but where we really see acetals is in sugars. That's really the important one. So for those of you that are going to go off to take biochemistry, I wish we had time to talk about biochemistry, but because of everything that's happening, I don't think we're going to have time to go over any of the biochemistry chapters. If we do, it would be for like an hour of one lecture. So hopefully we do, because I think people find it more interesting to see how organic chemistry applies into the biochemistry. But here's where acetals apply. So if you talk about a sugar, so everyone's kind of seen this type of structure for sugars. This is called a Hayworth projection. It's not really important to know the name of it, but just in case you're curious. All right, so they always show, that's kind of a big. So they always show a OH here. These are hydrogens right here. Okay, so that's usually how they show sugars, because they close up on themselves. Well, if you notice, this carbon right here, notice is a hemiacetal. You have an OH attached to it, and then you have an OR. Right? It's a cyclical hemiacetal. It's on itself, but it's still a hemiacetal. So sugars actually exist in this form, this hemiacetal form. Okay, if you took, oh man, sorry about that. Let me get this out of here. All right. So if you take sugar and hook it up to another sugar, 5-member ring sugar. This is fructose. I don't think I have the structure exactly right, but notice now this is an acetal. You have an oxygen attached to a carbon and another oxygen attached onto another carbon. Actually, this should be attached over there, but it's not important. But the important part is that you have a 6-member ring attached to another 5-member ring to form a acetal. Okay, so in sugar, in the case, it's attached to a glucose molecule and a fructose molecule. You have an acetal. So that's kind of where you see them. Okay. Also, just an interesting note, Glucose, as we know, is the common sugar for our bodies. Our bodies use glucose as its primary source of energy. And the question is, why glucose? Why is glucose the sugar? Because there's so many sugars. There's lactose, there's fructose, galactose. There's so many sugars. Well, I just told you that you form this six-membered ring, right? And we know that six-membered rings sit in chair conformations. Well, glucose is the only sugar where all of the OH groups are in the equatorial position. All right, so that's the structure of glucose in the chair conformation. Everything is in the equatorial spot. So our sugar in the our hemiacetal sugar, and then all of the other OHs are in the equatorial spots. Every other sugar has at least one or two OH groups in the axial spots. So those sugars aren't quite as stable. So glucose is the only sugar that has an all equatorial. So is that maybe why it was chosen? I mean, no one really knows for sure, but I kind of find that interesting. Maybe there is something to it, that glucose is the one that's been chosen by biology in everything, in every animal, as the primary source, maybe because glucose is the most stable molecule, and we have all developed enzymes and stuff like that to recognize that molecule where everything is in the ring conformation. It could also be that we get the most energy out of glucose because of the fact that it is in a ring conformation. It's the most stable of all the sugars because of the fact that everything's equatorial. So in order to break this apart, it has to release more energy in order to do that. So maybe that's the reason why. So I don't know if anyone really knows exactly why, but just kind of an interesting point. I'm trying to show you how stuff that we're learning that seems so obscure really is not. It's really important stuff when you start looking in biochemistry and asking questions like, why glucose? Why everything's equatorial? Well, I learned equatorial is the most stable. Maybe there is something to that or something. Okay? So just kind of an interesting tidbit. Okay. So there we go. Acetals. Here, acetals and carbohydrate. I didn't even know I had that slide here. Perfect. All right. So you can see in glucose, you notice everything at equatorial. Also note, I didn't talk about this, but since it's here, notice in cellulose. So cellulose is fiber. That's what cellulose is. This is fiber. Okay. Starch, obviously, is starch. Okay. Our bodies don't break down cellulose. Right? Cellulose is very strong. It's basically a bunch of glucose molecules hooked all together, where these bonds are acetal bonds is in the equatorial spots. Okay, so I'll have, another sugar here and another sugar, another sugar. So it's basically a whole bunch of these big chains of all these sugars, but everything is in the equatorial. All right, this is a very stable molecule, so it doesn't break down. Or if it does, it breaks down very, very slowly. So when we eat fiber, it basically stays like this until it really hits our liver. In our liver is where it starts to break down. However, it's not in our livers for a very long time. So only a very small amount of this actually breaks down. So you can't get a lot of energy out of fiber because of the fact only very few molecules break down. That's why they say that fiber is good, because one, it can kind of clean you out, but also it's a very slow, slow ingestion of glucose in your blood sugar. It's not like a immediate spike. It slowly adds sugar into your blood. Where starch is the same exact thing, except notice we have the oxygen in a axial position. Okay, so we know that if you have axial, it's more unstable. Okay, well, it's true. This molecule actually breaks apart very easily around that bond because it's very unstable, because I have this group in the axial spot. I don't have it in the equatorial. So since it's in the axial, pretty much as soon as it hits our tongues, these sugars start breaking apart immediately. Okay, because it's more unstable. So here on fiber, it breaks apart when it makes it into our liver. At that point, it's pretty much almost out of us. At this point, it turns into glucose as soon as it hits our tongues, because all these break. So starchy foods like a potato or corn or things like that, these start breaking apart very quickly into glucose on our tongues, and then by the time it hits our stomach, it's all in the glucose form, and then when it hits our liver, our livers have to deal with all of this sugar that immediately is in our bodies. So again, it shows you the axials are not stable. These types of molecules break apart, which is basically starch. If you just have another stereochemistry of that, so rather than having it in the axial spot, you have them in the equatorial spot, you now have cellulose. So as far as the structure, they're pretty much all the same, but axial versus equatorial, this is why we learn about it in organic chemistry, so that when you go to biochemistry, you can kind of see. Now it kind of makes, it makes sense if you learn about this now, where if you didn't know about axial equatorial, it's just something you'd have to memorize, and then also ask yourself, well, why is it? Why is it if this goes down, it's starch, and here it's not? Well, if you know the organic chemistry, understanding axial versus equatorial, all this should start to make sense now. Okay? So hopefully that was like a revelation for you. The universe just got a little bit smaller in your eyes. All right? So it's kind of cool. Now, again, I want to show you how all this stuff is not really obscure. It actually has a part in everything that we learn, the chair conformations and axial, and hemiacetals and acetals and stuff like that. Okay? All right, let me just talk about this one last slide, and then I think we'll call it a day, just because I want to make sure that everybody has time in order to get into that meeting if you want to go. So imines is another class of compounds. All right, imine is where you have, this is an imine, a carbon with a double bond to a nitrogen is an imine. All right, and the way that you make those is you basically take a carbonyl compound and an amine. All right, this kind of shows an intermediate. I don't care if you know that or not. It's not important. I just want you to know that an amine, and this has to be a primary amine too, meaning you have to have two hydrogens on it. Because notice you form a molecule of water. These two hydrogens and this oxygen pair up and form a water molecule. If you don't have a primary amine, you can't form an imine. All right, so it has to be primary. And they will react and you form an imine. All right, I don't know if they do a mechanism. No, they don't really show one, which is fine. Okay, let me just see. Yeah, they kind of show a mechanism. I'm not going to talk too hard, and then I'll talk about that tomorrow. Okay, so any questions? Anything you guys want to talk about? For those of you that came in late, if you didn't hear, I'm still grading your exams. It's going very slow just because of the fact that we post them online. It's not like I have them. Like normally, I'll just kind of I'll go through it pretty quickly. But since I have to